us now try to find out the power factor for sinusoidal voltages and currents. The power factor of sinusoidal voltages and currents are already well defined in the literature. Let us apply this measure definition and see if we get the same value, and then we shall apply it to the wave shapes of the rectifier, capacitor, filter, voltage and currents. Consider an oscillogram. X-axis is time, and let us place a voltage waveform on this. This is a voltage waveform, and it has a peak amplitude of Vm, and superimpose a current waveform with an arbitrary delay, meaning an RL load, and that delay is phi, and let the current have a maximum value of Im. So the voltage wave shape will have the equation Vm sin omega t. The current wave shape will be having Im sin omega t minus phi. So if you measure, now let's say this is the unknown load and you have measured something like this on the oscilloscope. How do you compare it with the pure resistive load? So let us say we would like to benchmark it with respect to a pure resistive load for the same magnitude of Vm Im. So let us draw the voltage having the same magnitude Vm, then draw the current. In the case of a pure RL load, the current has to be in phase with the voltage. Now retain the same magnitude as Im, and you have this picture that you would have got if it had been a pure resistive load. Now let us find out the powers. The instantaneous power curve we know is like this. There is some negative portion here for the RL load, and for the R load there is no negative portions. This is the average PR. This is the average P load for the unknown RL load. Let us move it up. Observe this negative portion. This is the reactive portion, and P load, what goes to the load, is the active portion. Now this is the reference resistive load. Now this value is given as Vm Im by 2. This for a pure resistive load. Now what is this P load? We have the reactive power component. P load is the active power component, and P load is less than PR. It is less than Vm Im by 2 because of this negative part. And if it is a sinusoidal case, we know that for sine waves, P load is Vm Im by 2 cos phi, where this is phi. So if we now apply our definition of PF is P load by PR, any wave shape, and for this special case of a sine wave, you will get cos phi. So it verifies that the definition that we have made as a measure of closeness to a pure resistive load. Any load, any unknown load, measure the closest to a resistive load will provide you the power factor value.